Okay, so recording started. We start our seminar. It's our first seminar in spring semester 2022. We start the seminars online, but some seminars will be in person. So, some of our speakers promised to come, but it's likely that it will be in May or in April, but unlikely in February and March. So our seminar today will be given by Patrick Marleaux from Technical University of Hamburg, and the talk is about so-called 2D+t theory, which is a technique to solve three-dimensional problems by using two-dimensional solutions, but quite sophisticated way. So that is the interesting technique for elongated structures, for like ships and high-speed vessels. So, Patrick, please start your presentation. But before that, I will ask all of our participants to switch off camera and microphones, and I also will disappear, but I will be here, and if something would be wrong, then I'll interfere. So I switch off my camera, and I'll switch off also my microphone. Patrick, please start.
Right, thank you very much, Sasha, for inviting me, and welcome everyone to my presentation, which is on simulation of high-speed chip hydrodynamics using a boundary element method and 2D+t theory. Now I will give you the contents first. I will have an introduction introducing my institute, me, and also give you a motivation on the method we are developing. I will give you a description of the method. Then I will show you some validation cases. The first will be on piston mode resonance. Then I will show you some examples of planing hull vessels, hydrodynamics being simulated with the method, and also some results on semi-displacement hulls, and we'll conclude with a conclusion. Okay, now let me first introduce our institute. So I'm working at the Institute for Fluid Dynamics and Chip Theory, which is located at Hamburg University of Technology. Yeah, our team consists of 3 professors, one of which is emeritus, and yeah, there's one chief researcher and 32 scientific employees, which are mainly PhD students, but also some postdocs, and 4 technical employees, which take care basically of the testing facilities. So there is a towing tank operated by our institute, and also a low-speed wind tunnel. And research areas include ship dynamics, such as maneuvering and seakeeping, ship propulsion, and as well as maritime renewable energy. And also there are some topics on optimization and innovative computational modeling. Now within the area of ship dynamics, there's a group located, which I belong to, that works on high-speed ship hydrodynamics. So currently it's Mustafa Abdelmaksud and me working on the topic, and there are also 4 more team members who contributed a lot to the current method we are having and research results we obtained, which is Hendrik Simonis and Jan-Philipp Soproni. And yeah, our main task is the development of Impact 2D, which is a simulation tool for high-speed ship hydrodynamics. And yeah, it is based on 2D+t theory, and it uses a boundary element method as a flow solver. And this kind of approach is based on methods which were published by Marilena Greco and TUHH Sun. So they're inspired by those publications. Now, some sample applications, what we are using this method for. In general, we can work on planing or semi-displacement hulls. These can be mono or multi-hull ships. And yes, topics are seakeeping, dynamic stability. We're also looking into maneuvering and most recently also in Arctic conditions. Okay, now I'd like to start with a motivation why it is necessary to have a special simulation tool for high-speed ship hydrodynamics. Now, in general, the importance of hydrodynamics increase with speed. Yeah, as you might know, the so there is a nonlinear proportion, and this makes some topics more relevant, like resistance and propulsion, dynamic stability, slamming, and seakeeping. They all become more important when the ship speed increases. At the same time, the complexity of hydrodynamics increase as well. So as you might take from this picture, you can see that the flow there's like a jet developing, and there's a lot of spray. And yeah, in general, there are a lot of nonlinear free surface effects. And there's also flow separation at the transom stern and also at the shines. And yeah, this is for this reason, like traditional potential-based methods, which linearize the free surface, usually don't yield in good results or any results at all. And then there are more sophisticated methods like a finite volume method, which can capture free surface effects like this, but they do cost a lot of computational resources. And especially if there are time demanding simulations like seakeeping simulations, yeah, this may be a problem. Now there's another feature of ships going very fast, and this is that the transverse wave system vanishes at high speed. And this allows for a simplification, and that results in 2D+t theory. And this, yeah, with this simplification, this allows to account better for those nonlinear free surface effects. And so this is basically the motivation to use 2D+t theory for high-speed hydrodynamics. All right, so now I start. Oh, sorry, something got. Very sorry about this. Just a second, please. Okay, here we go. I'm sorry. Now for 2D+t theory, the basics are the. Can you see the screen? I'm sorry.
No, not yet. Not yet.
Okay, I'm sorry.
Mm-hmm.
I have to share the screen again. I'm sorry.
Yes, please. It's coming. Yes, yes. It's first slide now.
Yes. All right, now.
6, slide number 6. Yes, yes.
Okay, very well. Okay, so 2D+t theory, the basics are the 3D flow is replaced by several 2D flows in Earth-fixed transverse cross-planes. So this three-dimensional domain is discretized by several 2D planes. And the method we use for flow computation is we use a potential flow solver and a boundary element method combined with a Mixed-Eulerian-Lagrangian approach to track the free surface. And this allows for fully nonlinear boundary conditions, which is an important feature at high-speed ship hydrodynamics. So here's an animation I'd like to show you to. I hope this goes quite okay over the internet. Now there is the ship hull which moves into the fluid domain, and it causes a flow in each of those cross sections. And you can see that this the time development in each of those cross sections yields also an approximation of the three-dimensional flow. Okay, now we come to some more details. In general, let's start with a 3D potential flow problem. So we're assuming that the fluid is non-compressible and the flow is irrotational. And then we can express the flow velocity with a gradient of a velocity potential. And the conservation of mass yields in the Laplace equation, which is the basic equation for our problem. And then we account for some free surface boundary conditions, which are the kinematic boundary conditions, which means that a particle on the free surface is moving with the flow velocity. And then there's the dynamic boundary condition on the free surface, which means that the pressure at the free surface is 0. And then there is a body boundary condition, which says that there is no flow going through the body. And now we make a assumption, which is that the total velocity potential, which is written down here, can be divided into a known wave potential and a potential that we actually want to calculate. So this is the potential due to the ship hull, and this is the known potential due to an external wave field. And this yields in a slightly different boundary condition. So now we have the external wave potential is also included in these boundary conditions. And now we make slender body assumptions. This means, we define a slenderness parameter, which is the beam divided by the length of the ship. And yes, we assume that the ship, this parameter is very small. And if this parameter is slow, we then assume that derivatives in x directions, which are proportional to this parameter, vanish as well. And this results then in all derivatives in x direction being neglected. So these are the background. Note that this assumption, like for the slenderness, it's a little bit vague. For example, it also needs to apply for the flow, of course, because this is where we apply it. And for example, if a ship is not slender but moving with a Froude number of 0.3, for example, then there is a transverse wave system which does have significant derivatives in x directions. So this assumption is more valid when the ship is going fast and the transverse wave system vanishes. Okay, so this assumption then yields in a 2D potential flow problem with the two-dimensional plus equations. And now I come to the solution method that we use to calculate this flow. So this is a general solution of the Laplace equation, which is based on Green's second identity. And it basically says that at any point within the fluid domain, I can get the value of the potential from the values on the boundary. And the values on the boundary are the potential and the normal derivative of the potential. And this equation is formulated for each node. And then we get a discretized form, which we can get an equation system from this, and then we can solve. Basically, what we can do with this equation is if we know one part of those boundary values, we can get the other part. So if we know phi, for example, from the equation, we can get phi n. So yeah, so this is how basically how we do it. We have our domain, and we divide it into panels, boundary elements, so to say. Yes, we apply the boundary conditions. So on there's the hull boundary condition right here, and then there next at the outer boundaries we just say there is the normal derivative is 0, and then we assume that we know the potential on the free surface. And yeah, this whole problem can then be solved with the boundary element method. Yeah, this is like one part of our solution. Like this is, so to speak, a boundary value problem we are solving. So we know certain values, phi n or phi, and we get the other values. Like we get phi n on the free surface, for example, and we get phi on the other boundaries from the boundary element method. The next thing is that we do is to solve for the free surface, because and this is a initial value problem. So we haven't used our free surface boundary conditions yet, and this is how we do this. So first we calculate the gradients using a local polynomial fit, and yeah, starting with some initial value for the free surface. For example, if you have a wedge-shaped body like this, we can take the Wagner solution, for example, as an initial solution. And then we go ahead and take our kinematic boundary condition. We can calculate this value from the gradients of the potential, which you calculated before using the boundary value problem. And then we move the node by integrating this value in time. And the same for the y direction. And doing this for every node on the free surface, we get a new shape for the free surface. And yeah, similar, it's done for the potential phi. We can calculate this value on the right side of the boundary condition, and then integrate it in time, getting a new value for the potential. And yeah, note this is done in a implicit way. So we explicitly integrate the kinematic boundary conditions. However, this can, or the easy option to do this implicitly, like then we can iterate again with the boundary value problem to exactly fulfill this boundary condition. And this is why this approach is also called implicit Euler, because we use a explicit Euler integration method for the kinematic boundary conditions and a implicit method for the potential. Okay, so for the next step would be to evaluate the pressure. So from the derivatives of the potential using Bernoulli's equation, we can get the pressure on the hull surface. Here, those the time derivatives of the potential are, there's a finite difference scheme which we use to calculate these. And yes, if we want to solve dynamic problems like sea-keeping simulations, we also have to solve the equations of motions. In general, they are like this. This is the math matrix. This is the acceleration and the forces. Yeah, it's like this. The problem is that these forces are also depending on the acceleration, and this is why we usually use we have to use the equation formulated like this. Now, this force does not contain the acceleration dependent part, but the acceleration dependent part is written like this, and also put on the other side. And this is also why it's called added mass. There's this coefficient. And this is just to make the simulation more stable. Yes, and then yeah, we can calculate the acceleration, and from the acceleration we can calculate the position by integration. Here again, there's the option that to explicitly update the displacements and implicitly solve for the velocities here, so that this equation is like more true because the acceleration is on both sides now, and we have to take this acceleration from the last time step at first to get the acceleration of the new time step, and then we can do this again to iterate it to get the exact or more exact equation. Yeah, so this is like a discretized form now of the equation of motions. Okay, there are some features, like this is basically the most difficult part of the method, which is to keep everything stable, because the free surface is very nonlinear and has can take some wild shapes, and there's a constant regridding and going on. So for example, this basically is done every time step where the free surface is regridded, and we use a local polynomial fit to interpolate values for the regridding. There's also jet and spray cutting, because if these jets maybe become too long, and then we cut it a little bit to keep it stable, or also the spray can get very long and maybe clash on the free surface here, so this is why it's then cut. This is to make the simulation stable, keep it stable. Yeah, also there's a separation model, either on fixed or non-fixed separation points. Like if you have a chine like this, it's a fixed separation point, then we always assume the flow will separate there. It's also possible if we have a round shape that there is a non-fixed, so we do not know the separation point. And then we take the pressure as a criterion, like hulls where the pressure is below 0, or another threshold can also be taken. Then those nodes will be turned into free surface nodes. And there's also the option if the spray becomes very thin, then if you look at the Euler equation, the pressure gradient will become 0, and then we can calculate the velocity directly using the Euler equation and do not need to use the boundary value problem for calculating the velocities. And there also possible that if flow reattaches to the hull, then those cavities, air cavities, will just be erased. Okay, now I'd like to show you the first case, which is about piston mode resonance. This is basically a validation case for the flow solver. So here is no 2D+t theory involved yet. It's a solely two-dimensional problem. And yeah, what we have here is a twin hull which is a semicircular shape. And here's a symmetry plane, so the same thing is going on the other side. And it's at zero forward speed. Yeah, we choose a certain distance of b to a 1.5 and two different motion amplitudes. So there are Heath oscillations that we are investigating here. I will show you just the small amplitude, but we also investigated larger amplitude. And what happens here is that there is a so-called piston mode resonance happening at a certain frequency. And this means that the free surface in the gap between the hulls is moving up and down very violently. So there has a much larger amplitude than the amplitude of the motion. And yeah, this is something we wanted to investigate to validate our code, but also to investigate this phenomenon a little bit deeper. So there are experiments which were done by Wang and Wahab in the 1970s, which we used as a validation reference. And we did simulations using our boundary element method and as well as a finite volume method. And we used two different assumptions here. Like on the one hand, we used inviscid flow assumptions, and then we used viscous flow assumptions. And the background of this is, if you look into publications on those piston mode cases, most of the times they're done with bodies with rectangular shape. And then there is a huge influence of viscosity because at the bilge or at the edge of those rectangulars, there's flow separation happening, and viscosity plays a big role there due to vortex shedding and so on. However, for a round hull like this, we do not expect to have much influence of viscosity, and yeah, we wanted to verify this, and yeah, we did the same setup with the finite volume method, just changing the assumption on the viscosity to isolate this effect. Okay, so here's a animation on this, just that you get an impression of what is going on. Here now in blue is the water and red is air. This is like the volume fraction from the finite volume method. And like in green is the boundary of the boundary element method. So you can see they agree quite well, although there are some differences in the details. So just that you know, you can barely see this hull moving. However, the flow in the gap is moving very violently up and down. And yes, the first thing we looked at are hydrodynamic mass and damping coefficients. Yeah, they are basically from a we get of course a time dependent results, and we do a Fourier analysis of those time dependent results, and from the first order Fourier coefficients we can calculate the hydrodynamic mass and the damping and compare those with the published experimental values. So here now in black are the experimental values. The black line is based on linear theory, as a linear potential theory, which was also published by the same authors as the experience. And in blue, there is our method, the boundary element method. And yeah, we did finite volume simulations for 3 different frequencies, which are the other markers. So you can see that the simulation results agree very well with the experimental results. There are some deviations in the lower frequency range. These are most probably due to oscillations of the end plates of the model, which happened in the experiments. So this may be a reason for those deviations here. However, for example, there is a very good agreement with the linear theory as well for the lower frequencies. And here at the resonance, so this is basically where the resonance happens, the hydrodynamic mass and the damping coefficient, they vary very strongly. And this variation is reproduced quite well by the method. and yeah, also better than the linear theory here. So here are some more details on the. We looked at the Fourier coefficients. We compared the Fourier coefficients from the different methods with each other. So the added mass and damping, they only relate to the first order Fourier coefficient, but there also are higher order Fourier coefficients playing a role here, although it's less prominent. And yeah, basically we get quite good agreement between all those methods. Yes, and yeah, some conclusion that we draw from those comparisons is what we find interesting is we can like the dependence of the phase angle on frequency, like the large like A becoming negative. This can be also explained, or it is a result of the if you look, this is the phase angle of the Fourier coefficients, and the phase angle, for example, at the low frequency, it's above half pi, and then it becomes zero. It changes with the frequency, this phase angle, and yeah, from this formula, the formula yields in a negative A if this angle is below half pi. Yeah, so there is a large deviation of this phase angle, and this what we also saw is that probably this large deviation is caused by the phase of the free surface, which is between those hulls, changing, and this is what causes the large change in A and B, basically. And yeah, another conclusion that we quote and draw is viscosity had a relatively low influence. And the differences that we saw between the boundary element method and the finite volume method are most probably due to the free surface. So the finite volume method has some better representation of the free surface, and some more details are covered, and we believe that this is the cause for the deviations. Okay, so the next case I want to show you is a planing hull. Now 2D+t theory is involved. And what we look at is our captive model test by TUHH in the 90s. And we have a mostly prismatic planing hull that we investigate. We look at here we look at steady forward motion in calm water, although he also at the experiments looked at other cases, like for example oscillating oscillations. And yeah, what we want to check is the variation of the vertical position of the hull and the trim angle, and yeah, see how good the method can reproduce the experimental results. So yeah, vertical force and trim moment were measured. So those are what we compare. And again, we do simulations with our boundary element method, and also did some with a finite volume method to check for 3D effects of the 2D+t theory. So this is what I like to show you here now. So this is a typical picture when you compare 3-dimensional results with the 2D+t results. So there are clearly some 3-dimensional effects here, and theirs are most prominent at the stern of the ship. So this is because zero pressure at the transom stern is not accounted for by the 2D+t theory, which is because we neglect all changes in x direction. So the 2D+t theory does not know that the ship hull ends after the transom stern. So this is basic, like this is the most prominent 3D effect, and it has a large influence, and there needs to be some correction model for this. And yeah, what we also, there are some additional 3D effects. Basically at the bow, this is due to pile up of water at the bow, but it's a little bit less prominent. And also at the shines, there is some 3D effects. Yes, what we investigated now is we looked at a relatively simple correction model, which was published in a paper by Sun and Faldensen in 2010. And this model is just just changes the integration boundary for the forces. So, and there is a one correction, the correction length parameter. For example, if this parameter is 0.5b, it means that we stop the integration of the forces right here. And like this force, this is ignored then for the whole force. So it's a rather simple approach, but yeah, we want to check how it what results can be given by if we use it, and yeah, we vary it this parameter to check its influence on the integral forces. Okay, so here is first the vertical force, and what we can see is that for zero correction, the force is too much, so there's is overestimated by our method. But yeah, as we can expect, if we increase this correction length parameter, this curve will move downwards, and yeah, there is maybe some optimum parameter here where we will get actually a quite good result then. And yes, on the right side is the variation of the trim angle. Yeah, and this is a similar result. In this plot, I use the same results. I use the results here from zero correction, but I shifted every. I just looked at the delta values, like on the differences from the initial values. Like you can imagine it like I put, like for this position, I put every curve on the same spot, and then I wanted to check how well the slope of the curve can be reproduced by each method. And we can see that the characteristic, like the slope, like the change of force due to a change of draft is reproduced very well, but there is some constant error, so to say. And yeah, for a variation of trim angle, it's a little bit different. So here you can see that yeah, the slope is also similar, but we can expect that the error also has some or that the trim angle has also some influence on the error, because this is not perfectly the same slope here. Okay, and now we look at the trim moment, and what you can see here is if you have no correction, we actually match the result from the experiment better than when we use the correction. And yeah, this of course is yeah, a little bit of a deficiency of this correction model. We cannot correct both we cannot correct the trim moment and the heave force at the same time, because we only have one parameter. And of course, if we change the integration boundary, we change both at the same time, the vertical force and the trim moment. However, it would be possible if we choose here a middle way to get a approximately okay-ish correction. Yes, the same thing I did for this for the trim moment. So we did again. It gets better for a change of heave than for change of trim. And yeah, another thing I like to show you is the resistance. This was not measured in the experiments, but I just used both computational methods for comparison. If you take the total force from the final volume method, it's way off the other from the boundary element method. But of course, there are shear forces in the finite volume method, and if we subtract those, so we get only the pressure-based resistance, then yeah, it's quite a good agreement. Yes, and the same phenomena are for if we take only the delta values. So what from those delta plots, one thing that we concluded from this is that it may be difficult to get an exact running condition if you only have the 2D+t theory-based method. However, we can expect that changes of the running condition can be reproduced quite well by the method, and this is why we think that this method is especially suited for dynamic problems. Like when the ship is moving, it changes its position, then we can reproduce or can reproduce the effects on the forces by those changes. Okay, I like to show you one example of a dynamic problem which was investigated some time ago, and this is porpoising. This is a dynamic instability, and it's basically a heave pitch instability, and it occurs if the center of gravity is too far aft. And yeah, I show you the animation. What happens? We have an initial oscillation here, and this oscillation gets amplified with time. So this is just a calm water case, and yeah, basically out of nothing, the amplitudes increase and it will become very violently. And this is something we try to reproduce. What we done here is the center of gravity was systematically varied, and it was looked if a initial oscillation would decline, then it's a stable case, or if it stays the same, then it's exactly the critical value which can be plotted in such a plot of a fruit number, for example. Yes, and now if you have a non-stable case, this oscillation will amplify and will become constant at a certain time. Now, one advantage, for example, there are also possibilities to do this linearized. So then you can say, is it stable or not? But if you would do it like this, it is a time domain simulation. One advantage is that you also can get this finite amplitude at the end when you get a steady oscillation phase. Okay, and here's some comparison with experiments. Those are not the same experiments I showed you before. These are by Day and Haag, quite old, and yeah, you can see they show the same trends. However, there is some like a constant offset. Okay, so let's go to the next case I'd like to show you, which is a semi-displacement hull. So this is the parent model of the high-speed displacement hull form series, which was investigated experimentally in the 1980s. Yeah, there was a segmented model used as well, which was used to get a distribution of the force over the length, which is very interesting for us as a validation. And the cases I show you here are the steady forward motion in calm water and free motion in regular head waves. And yeah, there were also a comparison of forced heave motions in calm water, which you can check in the paper if you are interested. Okay, so here's an example of the free surface shapes for two different fruit numbers. So it is 0.57 on the left side, and you can see there's some flow separation at the bow, but then the waves are quite low, rather small waves. However, for the larger fruit number, yes, there's also separation going on at the midship sections, and generally the waves are much larger and steeper. And yeah, here you can see a comparison of, first of all, here you can see the vertical force and divide it into its part, into hydrostatic part and dynamic part. And you can see it's semi-displacement hull, so both pressure parts play a role, but yeah, the dynamic part also plays for a significant role, especially at the bow. Yes, and here you can see the comparison of the dynamic force with the experimental values, and yeah, you can see it's quite a good agreement, except for the stern, because there, of course, we have again the deficiency of the 2D+t theory that zero pressure transom stern is not accounted for. However, it can be concluded it's a little bit less severe than for the planing hull. Probably because the ship is more slender, and is maybe one reason. Also, the dynamic force is not that large here. Yeah. Okay, so now let's come to the motion waves. First, an animation. Here you can see heave and trim motion, heave and trim, and the accelerations. You can see that this acceleration are quite non-harmonic, so which makes a nonlinear method, yeah, like that's nonlinear method gives you an advantage here, because yeah, linear methods only get you harmonic waves. Yeah, so you get an impression how it looks like. And those are the results of the transfer functions for the lower Fruit number on the left side, and for the higher Fruit number on the right side. You can see that the, like in blue here are the experiments, and those dots. No, I'm sorry, in blue are the simulation results, and those dots are the experimental results. And you can see they agree quite well. There's a little overestimation here at the peak by the simulations. You can also see that the simulations are better than those methods published by Bloch and Beugmann in the 1980s. Those are two versions of a linearized strip method. Yes, and for the higher Fruit number, the agreement is better between experiments and simulations. Yeah, so yeah, we are quite satisfied with those validations. Okay, let me come to the conclusion now. In 2D+t theory, the 3D flow around the ship hull is replaced by several 2D flow problems in Earth-fixed transverse crossplanes. A boundary element method is used as a flow solver, and this can be very efficient, especially compared to finite volume method. There are many nonlinear free surface effects which can be accounted for, such as separating jet flow, spray, and also piston mode resonance phenomena can be reproduced with the flow solver. And yes, this method is particularly suited for dynamics of slender, high-speed ships. Correction models for 3D effects need to be applied, and this is especially relevant for planing hulls. And yes, ongoing developments are validation for all 6 degrees of freedom. We are looking into maneuvering. We want to look deeper into dynamic stability. And yeah, most recently, we're also looking into the effects of level ice. And yeah, that was it. Thank you for your attention. And yeah, I'm looking forward to your questions.
Thank you very much, Patrick. Thank you for your presentation. Any questions? Any questions from our participants? Just a moment, I can see. Patrick, may I start questioning
Sure.
you? In slide 19 and 20, you showed so-called big L correction, I believe. So it was like 20% of beam, 90% of beam. Yeah. what's that? Yeah, you see the second line.
This one.
Found the element method L correction equal to 50% of BEM. What's that?
Yes, this is like the this is like if you take if we apply the correction model with this parameter,
Yep.
then the vertical force distribution will look like this. Like it will end not at the stern, but will end here at 0.5 B.
Yeah. But the does it mean that you just cut the force or pressures at the stern?
Yes.
Okay, so you just cut it. Okay,
yes.
And you make no corrections for the bow.
No, in this case not. No, this is
Okay.
like because it's a rather simple correction model, and they're a more sophisticated model as well. Yeah, but here we investigated this very simple model.
Yeah. Okay. So I understand. So indeed, it's very simple. Are there literature on that corrections of 2D+t sectional forces to make them better compared with the three-dimensional? I mean, what's other doing in this respect?
Yes, there are indeed. Like for example, my former colleague Jan Philipp Soproni, he did a lot of research on that, and he also developed his own models. Unfortunately, the thesis is in German. However, there's of course also other literature available. So there are, like for example, I think a paper by Game, which is often cited. I can maybe I can send you. I shall have it.
Okay.
And there you don't do such a hard cut here, but you do a mathematically approximation to get a similar shape like this. Yeah, but often when this is like the only one applied, then you have problems due to the other 3D effects as well. Yeah, but those are more complicated to correct.
Okay. So yes, please send me. I mean that kind of mathematical correction.
Yeah,
I see.
Yes, I sent you.
Yeah, indeed. I was confused that, but now I understand that you just disregard part of the calculated force close to stern. Okay, no correction for the bow. I see. I understand. And then in slide 23.
23.
Yes.
Yes.
Yeah.
Yes.
So that video. So I recognize that some sections they kind of enter water and exit from water when it starts oscillating. So yeah, you see, it's the section go up and go down. Down, enter water, and then exit from the water. So I understand you explained how you solve the problem when the a section entering water. But how you solve this problem when section exits the water?
Yeah, basically it's the same. So there's a boundary. The boundary values of the hull are always the hull velocity. So
right.
Yeah, you can look at, there's the rigid body, and then there are the cuts, like the earth fixed cuts, and yeah, then every time step we take a look where is the cut of the 3D body with the section. We can calculate the velocity of the hull surface in this two-dimensional frame, and then apply boundary condition like before. So also you must recognize here the view is now fixed with the ship. Yeah, that means in this video our calculations or our cross planes, they move. So
Yes.
they're not, and it does not necessarily mean that in a cross section that the hull really exits that big, because it's also moving forward, and there's also like this part of the velocity which is entering. Like when the ship hull is going in, but at the same time it does a pitch motion going upwards, then the, let's say, the velocity the cross section is entering with is reduced due to the ship motion, but it does not necessarily mean that in this two-dimensional frame it is as exiting.
Okay.
Yeah.
Okay.
But yeah, it can be the case. It makes it more difficult as well, because most of the jet cutting and so on, it's developed for entering, and then it can be more complicated to keep it stable. But from the solution procedure, it's the same.
Yes. But also it's that kind of exit stage, exit stages could be more problematic from point of view of stability of the solution. I think there could be a problem with that as well. Oh, yeah, it's my question. And any other questions, please? Okay, no. I have another question. So when your section, when you introduce vertical plane and you follow what's happening in this plane, so the section enter water and you calculate the elevation of free surface on both sides or on one side of the hull. And but it's possible potentially that the free surface calculated at next time step, it's intersect the hull. What you are doing in this case. So it's not necessary that the free surface is always kind of outside of the hull. It can go kind of inside the hull. I believe you showed the slide at the very beginning. Could be, no, even before that. Even before, when you explain how you update the position of the free surface and potential on it. Could be before 12 or 11. Yeah, that one.
Okay.
That one. The slide below. So you can see that each section, each node, you move up and horizontally, upward, horizontally, right?
Yes.
But it's so. For example, the point node on the hull. Yeah? So you show that it moves up. Yeah, that one. It moves up and then right. But you show that motion give you point exactly on the hull again.
Yes. It's unlikely that this is the actually result of the integration. You're right there. However, if it's not exactly in the hull, then we will just move it there, and then maybe if we move a hull, we have to also apply some corrections for the movement on the potential. So yeah, theoretically, of course, the velocity here should be like this.
Yes, tangential.
If you have an exact solution, then it should also be again on the free surface. If the integration yields, for example, the point being here, then it will just be the next nearest intersection to the ship hull in normal direction will be searched, and then the node will be placed there. Same if it's inside.
Okay. Yeah. So the you are saying that kind of theoretically the nodes always should be on the hull. Because that node you showed, this is the kind of material point. And you are saying that at next time instant, it will be at the tip of the jet or at the intersection point. So the same liquid particle will be there. So this is your approximation, right?
Yeah, not exactly. Like if we don't move it with this equation.
Yeah.
Like if we have to make a correction, like moving it somewhere else, then we also have to modify this equation a little bit, or this equation, because then it's not a strict material point anymore.
Okay.
So then you have to, I don't know the exact term right now, but yeah, for example, you have to make, account for the motion of the point then as well.
Okay.
This would be similar. For example, there are other methods where you don't move those points like particles. Then also the boundary condition look differently because you are having a pure Euler view on those grid points. Then,
yeah,
right.
Yeah. I assume the kind of main difficulties with to implement this technique is related, or half of difficulties are related to that intersection point, because the outside of that point everything more or less clear. So you just move the point and update the potential at that point. But at the intersection point, you need to adjust or to move this point, or also I understand the regrading or remeshing you are doing. It's also kind of related to that problems with the intersection point in particular. Not always.
Not only. Also, this is because also if you don't remesh, then with time it may happen that, for example, some points will accumulate and somewhere, or the grid distance will not be the same anymore. So this is one part of why also for stability it's better. So if you have some numerical small deviations, then you can smooth with the regridding. It smooths the free surface. It is also good for stability. But you can also introduce some errors if you do it too strong. If you do smooth too strong.
Yeah. So it should be kind of I understand it's not just what you showed, but there is a lot of experience behind it, how to use it and how it works.
Yeah, it can be sometimes it can be a real pain to get a simulation stable, because the free surface is doing it needs to be kept in the bounds that we can calculate with the boundary element method, which it wouldn't do physically. Physically it wants to go everywhere.
Yeah, thank you, Patrick. If there are no questions or any question, then the very last question from me. In this slide, on the upper figure, the distance between nodes is different. It's increasing with distance. So is it constant factor you are increasing the length of the panel, or?
Yeah, like we do it right now, is usually there is a constant element size on the hull, and for a certain part of the free surface also a constant element size. And then at a certain point, when it's far enough, then we increase the element size by a certain percentage, like 10%, for example.
Okay, 10%.
That means, like,
okay.
For example, this is just a parameter input for the simulation.
Yeah. So at some distance, starting from some distance from the hull, you multiply length of element by 1.1. Okay.
Exactly.
Okay. Good. So thank you very much. So now I'm more familiar how it's happening with the 2D+t, and I see there are no other questions. So then, Patrick, thank you very much for your very nice presentation and for your answer my questions.
Thanks for having me.
Yeah, thank you. It was good to learn from you how it works. So then I stop recording, and